There are several limitations associated with drawing Lewis structures for all of the molecules that we're going to look at in organic chemistry. So let's take a look at C5H12 as an example. Lewis structure here for the simplest constitutional isomer has all 5 carbons in a line. Then we have to draw in all of the hydrogen atoms. Okay, so what's wrong with doing that? Well, first off, it takes forever. For a lot of more complicated molecules like those you'd see in a drug, you can't do this. It's just too much work. The other thing, this doesn't show us anything about molecular geometry. So what can we do instead? We can draw a bond line structure. For that, basically we're going to have a zigzag pattern. I'll draw the structure for C5H12 and then I'll explain it. Okay, that's it. How does this work? Each end of a line or each vertex will count as a carbon atom. So we have 1, 2, 3, 4, 5 carbons. I'll go ahead and number them. Notice we didn't draw any of the hydrogens. If you have a hydrogen bonded to a carbon atom, it's an implicit hydrogen. You can assume that it's there and we just didn't draw it. Okay? This is important because you have to be able to recognize how many hydrogen atoms are still on these carbons. These are not just carbon to a carbon without a hydrogen. Okay? So you need to be able to look at carbon 1, for example, and say there are 3 hydrogens still here. We just haven't drawn them. Or at carbon 3, there are 2 extra hydrogens that aren't drawn. Okay, so how does this help us with geometry? Let's redraw the bond line structure for C5H12. Notice this zigzag pattern. If we do draw our hydrogen atoms, is reflective of a tetrahedral geometry. We could do this with each of the hydrogens if we really wanted to. It's a pretty ugly H. Let's straighten that out. Okay, we can add a hydrogen here, hydrogen here, hydrogen here. We can show the geometry if we want to. Okay, so the zigzag pattern is for a reason. But let's draw another constitution isomer of C5H12. Okay, instead of going all 5 carbons in a line, let's draw 4 of them in a line. Now we need to add a 5th carbon, so we'll just add a carbon right there. So how many carbons do we have total? 1, 2, 3, 4, 5. Okay, we could also draw this as that these are actually equivalent molecules. Why? Well, 1, 2, 3, 4, 5. The extra 5th carbon is still on carbon 2, this bond right here. In each case, all we've done is we've flipped this molecule over. So a lot of organic chemistry is spatial reasoning. Can you rotate things? Can you flip them? And that takes a little bit of practice. That's why molecular modeling kits are sometimes helpful. Let's take a look at C5H10 as another example. Okay, so we should know that C5 looks like that. C5H12 before, we had basically every carbon was fully saturated. It had as many hydrogens as we could. In this case, we've lost 2, which means we have a double bond. That's it. That's all this takes. So we count the number of hydrogen atoms. This carbon has 2. This carbon has 1, 2, 2, and 3. Okay? So if we add these up, we get 3, 5, 7, 10 hydrogens. Okay? It's very easy to take a look at another constitutional isomer just by drawing this again, moving the double bond. These are different molecules. This also helps us with our geometry. Let's take a look. If we draw in the hydrogen atoms here and here, notice that this bond right here is trigonal planar, just like an sp2 bond should be. Okay? We could also make a ring. We can make a 5-membered ring. We can make a 4-membered ring and add an extra carbon. We can add a 3-membered ring with 2 carbons. We could add a 3-membered ring with a chain with 2 carbons. Notice how fast that was to draw 5 or 6 different constitutional isomers of C5H10. Okay, what happens if you had a heteroatom? First off, what is a heteroatom? It is an atom that's not carbon or hydrogen. So oxygen, nitrogen, sulfur are typical heteroatoms that we would see. So C2H6O. The rule for heteroatoms is you have to draw them out, and you have to draw any hydrogens associated with them. Okay, so we have our 2 carbons. Let's draw those. 1, 2. We could say that's bonded to an oxygen. You know that oxygen makes 2 bonds, so it has to have another hydrogen associated with it. We can add the lone pairs. A lot of times I'm going to get lazy and leave them off. Okay, so this is the formula for ethanol, or is the structure for ethanol, C2H6O. Okay, if we count the number of hydrogens here, should be 3, 2, and this extra one, which is explicit, you have to draw it if it's on a heteroatom, gives us 6 total. You could also draw this like this if you wanted to, but that's a little bit complicated. Again, this actually shows us, though, the nice bent geometry of the oxygen here. We could also put the oxygen in the middle. Instead, just label it as an O. Here we've got 3 hydrogens. Here we have 3 hydrogens. These are both constitutional isomers of C2H6O, and they're much faster to draw than what we would see with a Lewis structure. C3H9N, easy enough. Let's draw our 3 carbons. 2, 3. Add a nitrogen. Nitrogen makes 3 bonds, so we're going to add 2 hydrogens to that, and our lone pair. Count the hydrogens. 3, 5, 7, 9. Just like that. Nitrogen is a heteroatom. You have to draw the explicit hydrogens. We could put the nitrogen in the middle of this. We could put it here. Again, we've got 1, 2, 3 carbon atoms. We would have a hydrogen here with a lone pair. We can count the hydrogens. 3, 5, 6, 9. Okay? I'm doing this pretty quickly, but the more practice you do, the faster you get at this. One more example, CH3CO, CH3. This is a condensed structure or semi-condensed structure. It's actually showing us a little bit. CH3C means we've got 2 carbons connected, double bonded to our oxygen, to a CH3. Oxygen, we can add the lone pairs if we want to. Okay, so CH3 right here, 3 H's. CO, CH3, 3 H's. This is a lot faster. Notice the geometry here is trigonal planar, just like you would expect an sp2 molecule to be. Your book has a fun example where they draw the geometry like this. This geometry should look off to you by the time you're finished OChem. It just should look fundamentally wrong. And why is it wrong? Well, the bond angles here are not 120 degrees. In the case where we've drawn it correctly, these are all 120 degrees.